All right. Hi, folks. Happy Friday, everyone. And hello, folks from around the world. Welcome to the 167th episode of the Qiskit Quantum Seminar. As is tradition, why don't you let us know where you're tuning in from in the chat? I highly recommend playing with the chat now so that if you have any questions you want to follow along with it, you use the chat, and I'll definitely use that chat to ask questions of our speaker today. To start, I'm Ed Chen, a research scientist here at IBM Quantum, hosting this seminar from Research Triangle Park, North Carolina. While people are playing with the chat, I just have a gentle reminder that this takes place every Friday at noon Eastern and will be hosted on this YouTube channel still. And we have a great lineup of speakers in the next few months. And thank you to our producers, Lako Minev, our video producer, Paul Searle, and managing producer, Olivia Lanes. Looking at the chat now, I see Juan from Colombia, Videsh from India. Wow. Yeah, Kenya, Monarch from India, California, India, Brazil. Awesome. All over the world. It's a really amazing group of people we have dialing in, and I think we usually notch thousands of views. Monterey, California, that's a beautiful place, of course. And today we'll be hearing from Zoltán Zimborás, who will be speaking to us about problem-informed graphical quantum generative learning. Zoltán is the head of the Quantum Computing Information Research Group at the Wigner Research Center for Physics and also a senior researcher at Algorithmic. He obtained his PhD at the UTVIS University in Budapest, worked later at University of Bilbao, UCL, and Free University Berlin before returning to Hungary. His fields of interest include the theoretical aspects of quantum computing, as well as the practical implementation of quantum algorithms on actual quantum devices. Being a member of the steering board of World Quantum Day and of Q-World, he is involved in various outreach activities. Together with his colleagues, he's developed new university courses on quantum computing that actively uses the online available quantum computer prototypes. Zoltán has asked that folks interrupt with questions in the chat to follow along, and I'll read your questions out loud at the appropriate times. Please, Zoltán, take it away.
Thanks a lot, Ed. And thanks for the introduction and the kind invitation. And this work that you can see the title of in my first slide, you can find also in archive. We put it on archive in May. And it's a work done together with two PhD students of mine, Bence Bako and Daniel Nagy, and also two fellow researchers from Ericsson Research, Peter Haga and Zsófia Kallus. So what is our topic? It's generative modeling. And of course, in the time of ChatGPT, generative modeling is talked about everywhere. What is it? Well, basically, we have to learn a representation of some probability distribution in order to generate realistic samples. It could be pictures of dogs or cats or sentences of the English language to talk about the ChatGPT. And actually, among the various machine learning applications of quantum computers, it seems that generative machine learning could be one of the natural applications. Why do I say this? Well, if you think about these typical supremacy experiments that show already for early quantum computer prototypes an advantage of quantum computers, they are based on actually producing some probability distribution, sampling from the probability distribution, which would be hard to sample from with classical methods. So this already seems that quantum machines would be a good fit for producing hard probability distributions. And obviously, because of this, there has been many work dealing with generative quantum machine learning. And here I just showed this at the upper right corner, this very nice table that you can find in Wikipedia about different type of interactions between quantum computing and machine learning. I will be talking about the interaction when we have classical data, but we want to produce or act with this classical data with quantum methods. So basically, I want to use a quantum computer, in this case, to learn a classical probability and produce samples from it. And I have listed here a couple of important highlights within generative quantum machine learning. And the one that I want to talk about mostly is the so-called quantum circuit board machine. be more precise, I want to, in some sense, redefine how we could do a quantum circuit board machine if we have some additional input about our model. So this is actually a very paradigmatic quantum generative model, this quantum circuit board machine, very general, and the name comes from that the probability distributions are generated by measurements, and those probabilities are given by the Born rule. So here you can see a schematic picture of what the quantum circuit board machine looks like. You start obviously with an initialization of qubits that are in zero, and then act with unitaries that have some parameters, so like a parametric quantum circuit, and then get samples from this. From these samples, if you have, let's say, only a few outcomes, maybe then you can look at the full probability distribution that you get, and then compare it with the probability distribution that you want to have, and use a distance, let's say, could be the total variation distance or any other distance between these two probability distributions, and then use that as a cost function. Obviously, if you have too many outcomes such that you cannot actually diagnose the full probability distribution, you just get samples. For example, if you have 50, 60 qubits, you will not be able to obtain the probability of each of the possible qubit configurations. Then what you can do is actually taking samples from your original probability distribution that you will want to learn, and from your circuit that you measure, and then use a maximum mean discrepancy, which basically gives you a measure of these. It's a measure comparing these two samples in a so-called kernel Hilbert space, and then you use that as the function that you want to optimize over. Okay, so I mean, most of the work have focused on these quantum circuit board machines, and they are like general purpose, meaning that you have, let's say, 4 random variables A, B, C, D, and you want to learn this is your task, learn the joint probability distribution of these random variables, and they could be obviously correlated. And often one does like this general purpose Ansatz, which means that you have 2 qubit interactions all along between any of the layers, connecting them, and then try to optimize the parameter according to the cost function. However, there is a big issue here, namely a trainability issue. In the quantum computing community, this trainability issue often goes under the name of bar and plateaus, meaning that while you are training your circuit, the derivatives becomes very low, very close to zero, actually exponentially closer to zero with the number of qubits. And this, of course, is a huge problem, because the way you train, if you have a loss function, is that you usually do a so-called gradient descent, meaning that you want to find the point where everything is optimal and has a zero gradient. But if in every direction the gradient is almost zero, you will not find the global optimum easily. This is called the bar and plateau problem. In some sense, this is deeply related to a very well-known folklore in optimization and machine learning theory. It's the no free lunch theorem. The no free lunch theorem states basically that you cannot have a general purpose optimizer or a general purpose machine learning algorithm that would have good performance for all machine learning model, all learning models, or all optimization models, meaning that they have poor average performance. And I would say that this is a very important fact, and I would highlight it because this is often not so much highlighted in the quantum computing community. The barren plateaus are, but the no free lunch theorem is not that much. It's very important, for example, if you work on, I don't know, quantum chemistry and variational quantum eigensolvers. I would say if you use the usual unitary coupled cluster Ansatz, which is a generic Ansatz meant for all quantum chemistry models, this will probably not work for all molecules. However, if you would have some problem-informed Ansatz, let's say the adapt unitary coupled cluster or other types of ones, there is more hope to do. This is similar in quantum machine learning. So what we did was to actually make some insufficient inductive bias. Sorry that I skipped over a slide. This slide was the no one model to rule them all. This is a usual meme in the machine learning community coming from Lord of the Rings, showing this no free lunch theorem. And so we don't want don't want a algorithm that would learn any probability distribution. We want to have algorithms that learns probability distributions when we have some knowledge about the probability distribution. So we want to have some inductive bias. And then there is a question how to incorporate this problem-specific knowledge. Well, we don't have to go long because these questions were asked, of course, in classical machine learning, and we will just use what they use. Namely, one of the simplest way of getting some knowledge about our distribution is asking questions about which random variables are independent from each other or how the dependency relations are. And using this, we will make a problem-informed ansatz. In other words, we use something which in the language of classical machine learning is called probabilistic graphical models. So here is like just a slide about the probabilistic graphical models. They usually say something with a graph, assign some independency or dependency conditions between the different random variables. I will come back to the mathematics of this in a slide. There are two big classes of this, the so-called Markov network and the Bayesian network. And there is also a mixed models. This is often used for various problems, natural language processing, sensor networks, where there is an obvious graphical structure or computer vision. And we want to use now quantum methods to build up a quantum circuit that has such an inductive bias in it. Going back to the math a little bit more, basically, here I show how we should imagine what a Bayesian network is and what a Markov network is. It's basically a property of the probability distribution. So for Bayesian networks, you have a directed graph, and the probability distribution factorized in a way where you have these conditional probabilities that you can see here. In a way that, for example, you can see that E only depends on B. So if you have the probabilities distribution of A, B, C, D, E, it is such that actually this factor only contains a probability of E conditioned on B. It doesn't depend on the other variables, only on B itself. Of course, B itself does depend on A. So you have this PBA. And PA, which doesn't depend on anything, has its own probability distribution. So you can write up these products. So we have to look, if you have such a graph, you can write up such a product, and we have to look for probability distribution that factorizes in this way. Markov networks, on the other hand, has a little bit different structure. We write a graph. This is not a directed graph. We look at the maximal clicks. Here there are two maximal clicks, the A, B, C. A click means a graph where everybody is connected with everyone. So the triangle, you are connected at all 3 points. And CD is another click, it's a small click. And you look for probability distributions that factorize it according to the clicks. So here the probability of A, B, C, D equals actually two factors. One factor is depends only on ABC and the other on CD. And you have to have a normalization here. Right. So, so here you have these factor tables. So what we want to do is that, once again, I'm just mentioning an example here. I give you the values of A, B, C, D. It could be 0 or 1. And for each of these values, I assign for A1, B1, C1 a value for phi 1, and for, let's say, C0 and D1 a value for phi 2, CD. So this one, and then I have to normalize. This is how you get your probability distribution. And actually we will randomly generate these factor tables, and then we'll look whether we can learn it with a quantum machine learning approach. Okay, so how do we do it? Basically, what we do is that we use a higher order Ising Hamiltonian. If you are, for example, familiar with QAOA, this is type of Hamiltonian, but here you have these ZZ terms, but here we can have multiple Z's over the clicks. So our first approach, which I show here, I hope you see my pointer. Our first approach was that we put I plus ZV, V is a vertex, and over all clicks, a product over these, and over each of the clicks, and then sum over the clicks. But from this, you can actually obtain a new Hamiltonian, where you have higher order Z terms. It could be a single Z, Z1 times Z2, Z1 times Z2, some Z3. I will give you an example. And each of these Z's will have a coupling alpha, and that will define a unitary, which is a parametric unitary, and this will be our parametric circuit. And after this, we do this parametric ZZ circuit unitary, we also apply a generic 1-qubit gate. And the initialization of our state is not 0, 0, 0, 0, but actually 0, 0, 0 acted with all the Hadamard, so it's a uniform superposition of all computational basis state. So I will give you a particular example in the next slide, but let me just compare with the usual quantum circuit Ising-Born machine approach. Well, it's very similar. It also uses a ZZ 2-qubit gates, and then at the end 1-qubit rotations. And we also start from after Hadamards, the uniformly uniform superposition of all computational basis states. However, we include other interactions, not only ZZ type of interactions, but ZZZ and so on. On the other hand, we don't include all ZZ interactions. So we don't have any qubit, it's not interacting with any other qubit, exactly because we have these independency relations. So let me show more concretely what we do. Here is an example of this graph that I showed previously with 4 nodes, A, B, C, D. These can be regarded as random variables taking binary random variables, so they take either 0 or 1 as a value. And what we do is that we look at each click. Let's say we look at the A, B, C click, and write up a Hamiltonian which contains all the Z terms where you multiply some subset of z's belonging to these vertices. So for example, ZA, ZB, ZC is one, ZA, ZB, ZA, ZC, ZB, ZC, and the single side Z. So you can see all of them here. And we assign a free parameter to this. And for here, we would have ZC, ZD. So this is the one. And then we exponentiate this. This will be 3-qubit and 2-qubit gates in this case. However, these 3-qubit gates, they are an exponentiation of a term with triple Z, Z0, Z1, Z2, these. And it's very easy to decompose this into 2-qubit gates. And this is the way how you do it, as I show it. Okay. So, of course, one way of doing it is that you can ask, can I represent any probability distribution with such a model? Of course, yes. If I take the full graph, then I have largest click, the full click, and it's a complete graph. Everybody is connected to everyone. And then I have all the terms. And of course, I can then with this circuit represent any probability distribution. But this doesn't sound very useful, and I will show it's not super useful. So our question is, when is our representation useful? And I have looked into some type of probability distributions. And here you can see we looked into 9-qubit cases. So when we have 9 random variables that are binary, taking values 0 and 1, and the independence relations are showed by this graph in the first one, like a regular rectangular lattice, or this rectangular lattice with these extra connections here, and also in the right-hand side, an even a little bit denser lattice. And what we see here is that if we try to learn such a probability distribution that we generated randomly with those factor tables that I showed, then in the first case, the quantum circuit Ising board machine actually performs not that badly. I mean, not that badly compared to our quantum circuit Markov random network, not random field model. You can see, I mean, here we do why we have 4 lines. This depends on the fact how we do what we choose as a cost function for the optimization. We can choose the KL divergence, Kullback-Leibler divergence, relative entropy, or the maximum mean discrepancy. These are like very typical things that you can choose from. And here you can see that in the first case, actually, the usual quantum circuit board machine performs well. The reason for this is that actually these correlations, like they have gates that are pairwise, they can capture very well these pairwise correlations. However, when you start to have clicks already that are like here you have the triangles form clicks in the second example, then also in the probability distribution you will have higher order correlations, and it's much harder for the usual quantum circuit board machine to Ansatz to get those correlations, while our model can get it. And on the other hand, we don't have that much parameters because we don't take into all connections, just the ones that are connected to the clicks. And in this third case, we have even more clicks, and you can see how the usual quantum circuit board machines performance decreases, while we still find very well the probability distribution, which is given by this total variation distance, the distance between the true probability and the ones that we learn. However, then you can ask, can we learn it well, or how well can we learn different probability distributions? Do we have, for example, this issue with the Barren plateaus? Okay, so we looked at this question, and we looked at into uh, different type of models. One is the complete graph, where we have the maximal click, and we have all the z terms. So we have 2 to the n degrees of freedom. And when we try to when we try to learn the cost functions variance actually decay exponentially, which actually means that we have a Barren plateau. On the other hand, for more less dense graphs, for example, we looked at uh, these triangle chains, which are very much related to the previous figures with the second one, but here we have chains and also random graphs. There we see actually on an algebraical decay of the variance, which could mean that we don't suffer in these cases from Barren plateaus. That would be a great example of problem-informed model not suffering from Barren plateaus. And I would say that although we don't suffer from Barren plateaus, and we only have poly n parameters in the circuit itself, it's classically still hard to produce those probability distributions. I will come back to it, and it seems that we have a good trainability for this using our approach, while the general quantum circuit Born machine won't have a good trainability. And so this means that we have a good efficient Markov network representation of these models. Let me also talk a little bit about the concurrent work, or also recent work that took the same approach as us. However, they didn't look at the quantum Markov random field networks. They looked at Bayesian networks, and they did something called the basis enhanced Bayesian quantum circuit, where they took a Bayesian network. Typically, this was the K-gram network, and added some 1-qubit basis rotations at the end, and looked at the probability distributions that can be obtained from this, and then have some certain property. They showed that this is more expressive than the usual classical Bayesian networks. This work I appeared in PRX in 2022. Gao et al. It came from the Sirac group. And what we were doing, if in classical machine learning, there are these two big cases of Bayesian networks and Markov networks. So Bayesian network is what treated quantumly in this work, and we treat the Markov network. It would be nice to compare these two. It's not so easy because one is about a directed graph, the other is about an undirected graph. But actually, there is a way that the Markov network can be put into a form of a Bayesian network. But I mean, it's rather computationally intensive task. It has to be triangulated. For example, if we have this Markov network showing A, B, C, D, this graph, we can do this triangulation and do and direct this graph in such a way that we get a Bayesian network. But then, of course, the Bayesian quantum circuit will require significantly more quantum resources than our network, the quantum circuit Markov random field method. But we tested it, and what we show is actually that although we had much less uh, uh, parameters for basically what we got is that we perform equally well as the quantum circuit, as the Bayesian quantum circuit of the Sirac group, you can see here. And what happens here, what you can see mostly is that the number of parameters. You can see the depth for them and for us. And for us, the depth didn't increase if we look at polygons of size 4, 6, 8, 10, 12, up to 18, while for them it increased the number of parameters and the depth also increased, and you can still see that our method learns as well as their method. But so this means that we have a similar performance at a much lower cost. I have to tell you, of course, that I mean, here is, of course, there is a little bit of a mismatch that we have to do this triangulation to get a Markovian network, but it's still when we can compare, then our method performs as well with smaller depth. So now we have learned that our method trains nicely. It doesn't contain that many parameters in many relevant cases, but can we get any advantage? Well, I mean, what do we mean by advantage? There could be many things when we talk about quantum machine learning. There could be quantum learning advantage when we learn the model in, for example, accuracy. We can learn it better. We showed, for example, that if we learn better than for certain models than the usual quantum circuit Ising-Born machine, we maybe there could be an advantage compared to classical model in learning speed and so on, or sample complexity, we need less samples. Well, probably the learning speed, there won't be too much advantage there, although it's a little bit unclear. But where we can say definitely is where we can have a advantage is in the inference. If you have learned some probability distribution, how fast can you get it? And we can show, if we look at the circuits that we produce, these Markov network circuits, these are in this Venn diagram, these are denoted by this green set or this green circle. This intersects with the Bayesian network, as I told you. But if you look at those circuits, actually it intersects also with um, uh, with certain the QAOA, which is a circuit for optimization, and it's unclear whether QAOA has a good advantage for optimization, but it's known that QAOA, sampling QAOA circuits is hard. So classically, to get the same distribution that the QAOA circuit produces for some values of the circuit, some parameters is hard. This was shown by several works. Here is one by Fari and Harrow. So this means, so our work is in this, if we look at in this shaded region, we know that actually there are some circuits where it's hard to sample from. Probably there are many of them. So this means that if the target distribution is learnable up to a given error by both the classical and quantum model, it could happen that, or it is probable that it happens that that sampling from the trained quantum circuit is more efficient. So the inference. I mean, if you think about ChatGPT, I mean, this is maybe not the good thing to think about. It's learning ChatGPT, a learning task is very hard for ChatGPT, but also to put out those sentences that we want in these larger models is also a hard task for which you need many GPUs. But it could be also, you could have also some other cases that perhaps the learning is not so hard, but putting out the samples could be a hard task. And in that case, we feel that there is a potential for quantum advantage. I mean, we cannot prove it, but we know that we have circuits that what we know is that we have these quantum circuit Markov random field models where the sampling from those would be hard classically. So they output probability distributions that classical methods would have hard time to output. Okay, so let's talk about what we found as promising in our method. Well, we have these higher order correlations compared to the Born circuitizing machine. So it outperforms this problem agnostic model, the usual quantum Born machine. And for many problems, for the most promising problem, we have only a polynomial number of parameters, and it seems that the variance of the cost function doesn't decrease exponentially. So maybe we can avoid Barren plateau, so it could mean a better trainability than for problem agnostic models, which seem to have a Barren plateau most usually. Although it's hard to compare with Bayesian networks, but if we want to compare, our method gives the same performance, but with less cost, like less deep circuits. And there are problems in our methods. There are probability distributions that are hard to classically sample. So there is a potential here for quantum advantage. Thanks a lot. And here you can find the QR code for our paper. And here are my co-authors. Thanks.
All right. Thank you, Zoltán. I didn't see any questions throughout the chat. If anybody has a question, please be sure to drop it into the chat. I had a very quick and probably naive question, but in the training over epochs that you showed,
Yes, here,
um,
yes. Yes.
I don't, I'm not quite following. So
What
you
happens here, right?
instantiated random graphs with random probability distributions, with
You mean in this slide, right?
yeah, exactly,
Okay, so
exactly.
what
So
we do here is, they are not random graphs,
okay,
but they are the
random weight,
graphs
random
that
distributions or something.
exactly.
Yeah.
So what we have is that so in this case, it's the probability distribution is very easy. It's a
Mhm.
product over 2-point probabilities that meaning or 2-point factors, like
Yeah,
factors over only two variables like
yeah,
this,
yeah.
and you have to apply them,
Mhm.
and uh, okay, we looked at this one, and this factor from the factor table that I showed you, we
Mhm.
randomly assigned some numbers to the
Mhm.
factor.
Mhm.
So these were
Mhm.
like randomly chosen probabilities that
Mhm.
we
Mhm. Yeah,
arrived to,
yeah.
and these were like small. Uh, I mean, it here you had like 5 qubits, and then here
Mhm.
you had
Mhm.
8 qubits, and so on. So there were some small qubit numbers, and what happened was that we could both compare the full probabilities because from
Mhm.
samples, because we had enough samples. These were
Mhm.
so these we trained with the KL
Mhm.
divergence, but we also did the case that would scale the maximum mean discrepancy,
Mhm. Mhm.
which compares basically the samples. And here what we see is that we have this epoch. So
Mhm.
each we learn and infer new values.
Mhm.
Sorry, and
That's fine. Yeah.
and we can see that it's roughly the same
Mhm.
as the Bayesian um, quantum circuit by the Dirac group. It has the same properties, but I mean our depth is much smaller.
Yeah.
Perhaps
Go.
I should also mention that classically there is an issue with training around Markov random fields, so these Markov networks. And the issue is that it's very hard to locally update the those those factor tables that you want to learn, because actually you cannot locally update it, because then also, or learn it locally, also this there was this
The hyper edges.
normalization factor
Mhm.
here, this 1 over z,
Mhm.
Yes, this is 1 over Z. It contains, of course, this is like this partition function, all the
Mhm.
sums of all these
Mhm.
phi 1, phi 2 products. So that
See.
brings in like long range coupling. In our question, in our model, since the quantum circuit immediately generates a probability distribution, this is automatically given, sort of. So we also believe because of that, hopefully it's not much harder to train than classical ones, and we get advantage in producing the probability distribution.
See. All right. Thanks for clarifying that point. And yeah, I like that you finish with these open directions of, uh,
Yeah,
yeah, and that should be very exciting for those students who are embarking on their quantum journeys
yeah,
in this field and where they want to tackle these next levels of
yeah.
problems.
So I would say that, like, as a last word, maybe that
Mhm.
often currently models based on or quantum circuit and quantum algorithms based on parametric quantum circuits
Mhm.
are not that popular.
Mhm.
And there are all these results about Barren plateaus and
Yeah.
so on. However, I would say that it's there are some reasons why they are not popular, but we have to be a little bit careful. If you have a problem-informed
Mhm.
parametric circuit,
Mhm.
that's good because you decrease the number of parameters.
Right.
The circuit is built up a little bit according to your problem, so you have some information. And maybe even you might have information about uh, how or not to choose randomly those parameters, but
Mhm.
in a proper way. Then all
Mhm.
these arguments that go into the theorems that show Barren plateaus will actually disappear.
Mhm.
Barren plateaus coming from noise is a different question. That might be a more problematic one that also appears in these
Okay.
cases,
Yeah.
but I would say that there is still hope for that. I mean, it's slight hope, but a hope for parametric quantum computation.
Got it. Okay. Thank you so much for your time. We really appreciate it. And before we sign off, people, next week we're off for holiday, and then the week after we'll have Professor Yoon Kim from I believe Cornell University talking to us about their her latest work. So thank you, Professor Zimborás, on telling us about your latest work. And if the folks in the audience have any questions, feel free to reach out, and I'm sure he'll be happy to entertain your questions. All right. Uh, thank you,
Thank
and
you.
everybody have a great
Thank you very
weekend.
much for listening.